Hello, this is Professor Kuehn. I've been discussing Book 3 of Newton's Principia. We've made our way up through Phenomenon 4, where he's describing the various things that we see regarding the planets that are orbiting the Sun. The specific phenomenon that we'll be talking about now, which I ended on last time, Phenomenon 4, I'll read it and then I'll explain what he means. He says that the fixed stars being at rest, the periodic times of the 5 primary planets, and whether of the Sun about the Earth or of the Earth about the Sun, are in the sesquiplicate proportion of their mean distances from the Sun. And as I mentioned in my last lecture, the idea here is that if you consider the Sun being, for instance, right here, and if you consider any 2 planets, let's take, for example, the orbit of, Mars and Saturn around the Sun. So let's put Mars right here, and let's put Saturn right here. That's a symbol for Saturn, that's a symbol for Mars. And if you were to measure the time of orbit of Mars and the time of orbit of Saturn, you were to find this ratio of their times, the periodic times. Those are in the sesquiplicate proportion of their mean distances from the Sun. So if you think about their mean or average distance for the Sun, you might think about that as the radius of the orbit, the distance of Mars from the Sun compared to the distance of Saturn from the Sun, and like he says, in the sesquiplicate ratio, the 3/2 power. They're in the sesquiplicate proportion of their mean distances from the Sun. Okay, that is the point that he's making here. How does he know that to be the case? Well, he provides us the data in table 26.3, which I've reproduced right here. This is a comparison of the observed sizes of the planets to their calculated sizes based on Kepler's third law. Remember, this here is Kepler's third law. So essentially, he is going to argue based on the data that the planets in their orbit around the Sun obey Kepler's third law of planetary motion. Let's just kind of look at this table to make sure we understand. So this is a symbol of Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Those are the traditional astronomical symbols. So these are the periodic times with respect to the fixed stars of the planets around the Sun, measured in days and decimal parts of a day. So if you imagine the stars, which are way out here, he thinks of them as being fixed. They're the distant stars. They're not moving in Newton's theory. Okay, the Sun is again not moving. It's like one of the stars in that respect. The planets are going around the Sun. It takes Mercury 87.962 days to go around the Sun. Venus, it takes 224 days, about 7.5 months to go around the Sun. The Earth, I don't even know why I'm squaring these off. I'm just not going to do that. Earth takes 365.2565 days to go around the Sun. Mars, 687 days. Jupiter, 4,333 days. And Saturn, 10,759 days to go around the Sun. So we could take any of these two, like Mars and Saturn, and form the ratio of the number of days there and the number of days there. That would be the left-hand side of this equation. Okay? Now, down here, he's giving us data on the mean distances of the planets and of the Earth from the Sun. It's not quite clear what units he's using, but here he's got the Earth. According to Kepler's data, it's 100,000 units of distance away from the Sun. Again, I don't know what the units are he's using, but he's using some kind of standard. According to Borealdus, it's 100,000 right here. So this is the experimental data, the first 2 rows. Using the same units, Venus is 72,000 units of distance away from the Sun, Mercury is 38,000, Mars is 152, and so on. What you could do is calculate the expected value using this formula of the distance from the Sun of each of those planets. So we can calculate it using Kepler's law, the periodic times, as these ratios to compute what the expected distance of Mars would be from the Sun by using Kepler's third law. So this is the calculation of the distance using Kepler's third law. And you'll see that these numbers lie pretty close to the measured values of the distances from the Sun. And so what Newton is essentially arguing here is that Kepler's third law holds. That is, the planets are obeying Kepler's third law. And again, this is going to be important because this is going to imply, and this is what he's going to argue in the next chapter, that there is a force, a centripetal force acting on the planets, and it goes as 1 over the distance squared, where r is the distance of the planet to the Sun, and that's what I've referred to as a right there. Okay, so that is phenomenon 4. Okay, let's talk about phenomenon 5 and then 6, and then we'll be done with this chapter. So what is phenomenon 5? Actually, let me go ahead and import it. Image. Phenomenon 5. Let's put it right up here. Okay, I'll read it first. What he says is that the primary planets, by radii drawn to the Earth, describe areas in no wise that is not proportional to the times, but that the areas which they describe by radii drawn to the Sun are proportional to the times' description. So in other words, what he's saying is, if you draw, on the one hand, if you imagine the Earth to be at the center of the universe, and you look at the motion of Mars through the sky, and you draw a radius from the Earth to Mars, you're going to find that you do not get an area by radii drawn to the Earth. The areas are not proportional to the time. But on the other hand, if you consider the Sun to be the center of the universe or the solar system, and you look at the orbit of Mars around the Sun, and you draw a radius to Mars from the Sun, and you look at the area that it sweeps out, in that case, you'll find that the radii drawn, the areas which they describe by radii drawn to the Sun, are proportional to the Sun, to the times of description. The main point he's making here is that he's referring back to his proposition 2, theorem 2, which, remember, he said if something is orbiting around something else and the area that it sweeps out is proportional to the time, that implies that there must be a centripetal force acting toward that central point. So by this, he's going to argue that Mars is not feeling a centripetal force toward the Earth. So Mars is not governed, its motion is not governed by a centripetal force toward the Earth. Rather, its motion is governed by a centripetal force toward the Sun. Or if there is a centripetal force toward the Earth, it's negligible. It's very small compared to the centripetal force it's feeling toward the Sun. That is what he's getting at in this phenomenon 5. I don't want to spend much more time on that one. I just want to roughly or quickly mention it. And then let me just say one other thing. Let me talk about his phenomenon 6. Okay, here it is. Phenomenon 6. I'll read it. That the moon, by a radius drawn to the Earth's center, describes an area proportional to the time of description. So if you draw the Earth, let's say right here. So here is the Earth. Okay, so here's the Earth. And if you were to consider the moon and the orbit of the moon around the Earth over the course of about a month, and if you were to draw a radius from the Earth to the moon, and if you were to consider a particular time interval that it moves from here to here, so that would take, you could sweep out a certain area. So this would be area 1 during a time t1. And if you were to, again, think about if you were to double the time, so you're to figure out the area in double the time. So this, I guess we could do that area, so area 2, and it is time 2, you'd find in twice the time it sweeps out twice the area. That is, the area is proportional to the time, or it sweeps out equal areas in equal time increments. Those are all the same kind of statement. So the moon, if you draw one of these radii by a radius drawn to the Earth's center, describes an area proportional to time description. And again, the main point is that this is going to imply that there is a centripetal force acting on the moon toward the Earth. That's the main point that he's making here. So all of these phenomena that Newton has been discussing in chapter 26, all of these he's going to use as evidence that there are these centripetal forces pulling objects like the moon toward the Earth, like Jupiter and Saturn's moons toward Jupiter and Saturn. There's a centripetal force that is pulling the planets toward the Sun, and all this is going to be used as evidence for his universal law of gravitation.